Hello, this is Robert. Today we'll investigate another Calculus 2 topic dealing with infinite sums, infinite series rather. Here's an infinite series. You might recognize the type of series this is and some of the methods involved breaking it up and investigating it more deeply. Now what we want to do here, this question is actually asking us, this is pretty typical in 10.3. Lots of homework problems are going to ask you to find the formula for the nth term. We'll talk about why this is sequence of, so don't worry about that for right now, of the sequence of partial sums. So what we're looking for is a partial sum of this infinite series. So rather than an infinite number of terms, we'll have n terms, right? That's what this represents. N terms, number of terms. Okay, so we want to have a formula, S of n, that goes from something to n, right? Let's talk about what this is. And we want this to be in terms of n. This has n type stuff in it. N's and n type stuff. N's and numbers and things like this. This is what the formula will be. This is what our goal is. Okay. But what we want this to, what this means is a sum of n terms. First n terms. So if we started at 5 and we said let's let n equal 6, that's 2 terms, not 5 terms, and this would indicate s of 5 would indicate the sum of 5 terms. So that's not going to work out. If we started at 0, we won't have 5 terms either. If we went to 5, we would have the first, we would have the k equals 0, 1, 2, 3, 4, and n equals 5. We'd have 6 terms. So this isn't going to work out. So what we need is for our summation to start at n equals 1. Okay, we want to represent our partial sum as s sub n. If we want to represent it as s sub n or report it as that, then we just start at 1 and go to n. That's going to give us n terms. So let's figure out what this is going to be here. All right, so how might we do this? All right, well, we first see that our original doesn't start at 1 as we need it to. So we need to do a little work on this. So let's go ahead and increase the index, something you can do if you know what's going on here. We increase the starting point. We need to step back each of the k's inside of the formula. That's all you have to do. Step these back. Okay. So we increased it by adding 1 to the value of the starting point, so we're decreasing each of these k's. Now all you need to do really is be super careful, do this properly. I did one like this earlier and made a little mistake in here, and I didn't find out I had made a mistake until, 2 pages later, right? So be super careful on how you do this. So when you're replacing a k with a quantity, just literally put it in parentheses and then do the math. Try not to do too much at once. So let's go ahead and work this out. So now we start at 1, which is what we were hoping for. And now we have a 3k minus 3. 3k minus 3 plus 1. Minus 3 plus 1 is minus 2. And then we have a 3k minus 3 plus 4. 3k minus 3 plus 4 plus 1. All right, here we go. Here we have our infinite series starting at the proper index, getting it set up to expand this and find our partial sum that we're looking for, right? This is what we're looking for. Okay, a sub k. There we go. That's what we're looking for. So let's find our a sub k. So how do we do that? Well, now we recognize this as a rational function. This a sub k is a rational function which has the denominator has 2 linear factors. This is what might pop into your mind, hopefully by this time, is that this can be expanded out into simpler individual terms, individual rational terms with single factors, denominators. And when that happens, this might turn out to be a nice telescoping series where we have quite a lot of the terms canceling out. Sometimes all but the first two and the last two terms cancel out, or the first three and the last three remain, or maybe even the first term and the last term remain and that's it, and everything else cancels out. So how do we know, how are we going to figure that out? Actually, literally just write out some terms, that's all. Oh, no, we can't do that yet. Getting ahead of myself. We need to break it up using partial fractions. So you remember in Algebra 1, you took individual fractions, individual rational functions, and we found common denominators, and we combined them into a single rational function with a common denominator. Well, this technique is actually just going in the exact reverse direction. We're taking a rational function that has a common denominator, and we're breaking it up into individual partial fractions. And so now all we need to do is figure out what constants go up here. Well, we don't know that, but there's a method of finding it out. It's called the method of partial fraction decomposition. This is what we're going to do right now. Actually, a couple different methods that I've used, I see students using. So I'm going to actually just go through both of those methods, and they should match up. The beauty of math is it doesn't matter the method you use. As long as you're doing steps correctly, you get the same answer. And so when the factors are linear and they're non-repeating, meaning multiplicity of 1, this only occurs one time in the denominator, then we just need a constant on top. Same thing, linear, not quadratic or higher degree, so we just simply need a coefficient b on top. If it were repeating, then we have another method where we just add on more terms here and we step up the denominator power. So that's it. So we need to figure out, solve this for a and b. Okay, easier said than done, right? Well, it's not too bad actually. So let's go through the two methods. In both methods, the first thing you need to do is multiply both sides by the common denominator, which is this. If I multiply this side by this, I get 1. If I multiply each of these terms by that, then I get different kinds of cancellations. This will give us an a, 3k plus 1. These two things times this term, we have this guy cancels. So we get b times this guy. Alright, now here come the two methods. Method 1, I like to think of this as old school because I learned this in school. I'm old. Kinda. Okay. That's the starting point. So let's go. Method 1. Method 1, we're going to find a system of coefficient equations, a system of equations, right? If you like solving systems of equations by elimination or substitution, this is your method. Let's make sure we did everything right. Okay. So what you do is you basically multiply out your equation and cluster up like terms together so that you can factor out k's or k squared terms, factors rather, and etc. So here I have 3ak plus a plus 3bk minus 2b. There we go. We've clustered up like terms so that we can factor out k's. And let's go ahead and group up our coefficients. If you like parentheses to make them appear as a group, you can. That's perfectly fine. There's not a subtraction sign in front, so this is legal, mathematically equivalent. And now this over here, what I like to think about is, okay, see, what we have to do is compare coefficients. We compare the constant term to the constant term. And we compare the k term to the k term. This doesn't have a k term, right? For this equality to be true, this coefficient must equal the coefficient on this side for the k, right? These coefficients are equal, and then these constant terms are equal. So 3a plus 3b must equal 0 for this to be true. But not only that, and simultaneously this needs to be true, that this constant term equals that constant term. So here we have it, system of equations. You can solve this in any number of methods. Let's go ahead and multiply through by -3, right, times -3 through the bottom equation. And let's rewrite it. -3a plus 6b equals -3. Rewrite, simply stack your equations and add. All kinds of ways to solve that. But here we have the elimination that we were looking for, and then we just solve. B equals -1/3. Okay, now we go up to either equation, any equation we want, our new modified one or one of our originals. I like this one, personal preference, because it's real easy to see that 3a equals -3b, meaning a equals -b. Now we substitute in negative to 1/3, -1/3 to -b, and we get +1/3. So this should be the match up with the answers we get in method 2. Now method 2 I learned from students several years ago, which is one of the reasons I absolutely love tutoring and teaching, because I'm constantly learning new techniques, learning new ways to look at things, different ways of looking at things. It's just super fun. So I highly recommend it, teaching and tutoring. But here we start with our original, and we just let k be some number arbitrarily that will force one of these coefficients to be 0, or actually one of these quantities that multiplies our coefficient a to be 0, right? So -1/3 is a prime choice. -1/3 times 3 is -1 plus 1 is 0. That goes away. Now what would be, in this case, we'd have 1 equals 0 plus b times 3 times -1/3 is -1 minus 2. So we get -3b, which b equals, divide by -3, hopefully the same thing. Yep. And now if b is -1/3, oh, okay, let's just stick with this method here. So now we're going to let k be something different so that the b goes away. Well, -1/3, no, -2/3 would have to be what we choose, because -1/3 would give us -3, right? But no, not negative, +2/3. +2/3 would give us +2 minus 2, 0. So that's what we need, +2/3. So what's a going to be? +2/3 times 3 is 2. 3a equals 1. +1/3. So there we have it. So now we have our coefficients. We've broken up our summation. Now all we need to do is write out our summation. Let's see, k goes from 1 to infinity of 1/3. Really careful here. Plus minus. So -1/3 is b, 3k plus 1. Now we can telescope this guy. So let's step up. Let's plug in a few terms here. When k equals 1, we have 3 minus 2 is 1 times 1/3. We're just going to go like k equals 1, k equals 2, k equals 3, and we should see a pattern by then. If not, we can do some more terms here. Oops. Okay. Come on. K equals 1 at 3k plus 1. We get 3 times 1 is 3 plus 1 is 4. So k equals 1, we get 12, right? Minus 1/12. All right. So now we have a cat in the way is what we have. Carry the cat. That was a stupid joke. Okay. K equals 2. We have 6 minus 2 is 4. 1/12. Yay, this cancels right away. I like to see that. Sometimes it takes several terms. K equals 2. We have 6, 7, 21. All right, k equals 3, hopefully 21, right? 9 minus 2 is 7, times 3 is 21. And minus, so this is enough terms. 3 times 3 is 9, plus 1 is, so we get is 10, times 3 is 30. And we can see that